Hello, and welcome to Network Collective. We're here again today to discuss the nitty-gritty of data networking. But before we dive into today's topic, I wanted to give a shout out to our friends over at Gestalt IT who started a new podcast that they're calling the On-Premise IT Roundtable. If you caught the play on words there, good for you. There, you'll find conversation about networking, storage, big data, and other IT topics in video and audio format. We will put a link in the show notes, so go check it out. For those of you watching live, you can tweet Network Collective to participate in the conversation. And now we're going to get started. Today, we're going to do a deep dive into EIGRP with two storied routing experts, Russ White and Nick Russo. Nick, why don't you start us off by telling us a little bit about yourself?
Hi, thanks everyone. I'm really happy to be on the show. My name is Nick Russo. I'm a network consulting engineer at Cisco. I've been working in networking for about 7 years, and the first network I ever worked on was a large EIGRP network when I was deployed to a combat deployment in Afghanistan. And since then, I've been working with it pretty extensively over the years. And I've done two designs that I'll talk about in this show pretty recently that I think kind of highlight some of the capabilities of EIGRP as well as some of the challenges that we encountered during those designs.
Great. And Russ?
Hey, Yvonne. How are you tonight?
Great.
I'm Russ White, and let's see, I work for LinkedIn. I've been doing networking for about 30 years, and you can always find me at rule11.tech.
Good deal. All right, let's kick things off. Let's start by just talking a little bit about a few of the best use cases for EIGRP. Most of us, if we've worked on a network with Cisco gear, have touched EIGRP, but today, what are some of the best use cases for that as our IGP?
IGP.
Yeah, GRP, IGRP.
Yeah,
sorry,
like
I was having
IGRP.
screen problems and I was trying to dual thread and it didn't work.
Oh my goodness, bad memories.
At least you didn't say EIGRP, Yvonne.
You just had to do it, Phil.
Wah, wah, wah.
We are off the rails 30 seconds in. All right, guys, use cases for EIGRP.
Hub and spoke is a really good use case. I actually think data center fabrics are a good use case, although we never see them there. Any kind of hub and spoke. And actually, I think any sort of campus network where you kind of want to fire and forget. The problem with the EIGRP is unlike the four-letter protocols, I don't let my kids talk about four-letter protocols.
Oh.
But anyway.
And you make fun of my jokes?
Sorry. So the problem with the EIGRP is I like to call it a cliff protocol. It does not, like OSPF and ISIS, when they degrade gracefully and slowly over time. EIGRP, when it fails, it's gone. It's dead. Forget it. It'll never converge. So it's like it gets to this point where it just collapses. So I think that EIGRP is really good in these situations where you kind of want to fire and forget, but it's a limited scope unless you're going to do real design. If you're going to do real design, EIGRP is a terrific protocol for just about any network, I think, unless you need link state for some reason.
All right, so you piqued my interest there. Under what conditions does EIGRP just go off a cliff?
Oh, Yvonne, bad memories, all sorts of bad memories here. So typically EIGRP runs into a couple of situations where it goes off a cliff. Now, the SIA rewrite solved a lot of the problems that I've encountered in the field over my years of working on it. But typically what used to happen a lot was when the query chain became longer than the neighbor adjacency hello timer or dead timer, it could cause all sorts of problems with SIA, and that would cause the protocol basically to go off a cliff and never converge. Another thing that I've seen happen with the EIGRP is, let's say that you have your max paths set in your routing table to 8 paths, and for whatever reason, you built a network with 32 alternate paths everywhere. Well, EIGRP being distance vector won't try to install all of them. In fact, it only advertises what's in its local table. So now you have this weird state where you have 32 available paths, which EIGRP can churn on, but you're only advertising 8 of them. So you get into these churn situations where things just go nuts. And so quite often when I would work on a very large scale network with EIGRP that was collapsed, the first thing I would do is go around and find every network pair of paths or whatever in the network where I had more paths available than the max route set in the routing table, and just start setting passive interface everywhere and cut the number of paths down. And that would usually stabilize EIGRP. So those are the kind of things you can get into where it tends to fail. Beyond those types of things, though, EIGRP tends to be very rock solid. I mean, I've seen it in hub and spoke networks with 1,200 to 1,500 remote sites and 2 hubs, and it just runs perfectly fine. The whole network can go down because of a link failure and come back up, and it's perfectly happy, particularly after the stub stuff was put in and the SIA rewrite stuff. I mean, it's an extraordinarily stable protocol by and large.
I do. I mean, I'm just looking at or in listening to those cases where it doesn't work. Those seem awfully point. You know, like
yes.
Yeah. I mean, most networks aren't that. Most networks don't have more paths available than
what you have
maximum paths. In the EIGRP set. So I mean, I can see that. I guess you would have seen more than most of us. So I'm glad you shared those. But,
the TAC case that wouldn't end is what I'm hearing.
Yeah, that's kind of the take I got there too.
Yeah. Well, global escalation more than TAC, but yes, that's exactly right. When you get mailed on site because the network won't converge for 6 hours, then you suddenly start figuring out how to make it work again.
Yeah, so I got something kind of to clarify. I think where Russ hit a lot of really great points with that, but just to maybe illustrate this for people who may not have caught on to some of those immediate use cases. So one of the first things Russ talked about was data center fabrics, and we think of a traditional data center which has big chassis switches at the core and aggregation with maybe fabric extenders or top of rack switches and a bunch of layer 2 ether channel multi-chassis link aggregation. That's kind of a traditional DC. That's not really what Russ is talking about in this case. What he's talking about is kind of a routed leaf spine style of fabric where top of rack switch is really a router with a whole bunch of uplinks to a whole bunch of spines. And that's kind of the case where you end up with 32 ECMP paths between all the different spines. Right. And that's kind of the case where just to kind of clarify that for people. And the reason, and now to touch on that max paths 8, just to give a little clarity for people who may not, the distance vector nature of the EIGRP causes that problem, because if I have 8 routes on my routing table and there's 24 other paths I'm not using, if I lose one of those 8 paths, it's feasible that the reachability to that route that I lost could be reachable through one of those other 24 neighbors. Because if I didn't install the route from them, then I'm going to query them. And that's part of the big issue, is that you either turn off EIGRP neighbors or do some kind of filtering, which we can talk about a little later, or increase your max paths.
Passive interfaces, something else.
Yeah. So the real takeaway there is, by having your max paths too low, not only are you not using all your available paths, but you could actually be causing very serious convergence problems for the protocol. And those are some interesting pitfalls that would come if you had a data center type fabric using EIGRP. And right. To Russ's first point about Hubspoke networks, if you think about the top of rack switch as it relates to the spines, it's kind of like a spoke with a whole bunch of hubs. And when you look at the design that way and you apply the Hubspoke principles to a data center fabric, naturally EIGRP stub tends to make sense on top of racks. So a lot of those EIGRP design use cases that you would do in a Hubspoke WAN make sense in those layer 3 routed data center fabrics as well.
So why do you guys think that that's not necessarily a common use case for EIGRP? Because I don't know if it necessarily is. I don't see a ton of white papers where that's the routing protocol of choice in a DC fabric.
I actually don't know of any that are deployed today. And I think the reason is because people tend to either want to do traffic engineering, so they want a link state protocol, or they just fall back to the old standard of BGP, which, we can go back to the whole BGP discussion, right? And how we tend to overuse that protocol and we don't tend to use the other tools we have in a toolbox. And EIGRP to me is a perfectly valid tool in the toolbox for the right situation. And, we should just use it where it makes sense.
That's interesting. So I know, Nick, you said that there were a couple other use cases you wanted to talk about. Are there other scenarios or interesting EIGRP networks you've seen that you've got in mind?
So I think the first words that Russ said, when you say hub and spoke network, that covers a lot. And the two specific designs I worked on were both hub and spoke style of network. So I'll talk about one that I think is particularly interesting. The second one's more of a traditional enterprise WAN use case. It's a little less fun, but I'll talk about the one that was kind of interesting. This was a case where we were deploying little routers that had LTE uplinks back to LTE and Wi-Fi uplinks, so one of each basically back to a head end that was some short distance away. And what we needed to do, the only purpose of this network was to be a transit network for clients that plug into the LAN side of those little routers that have little switch modules. A client plugs in, and that client opens up a remote access VPN to a concentrator somewhere behind the head end. So you think about the traffic flows in that environment. It's really a true hub-spoke network with absolutely zero requirement, or put it this way, no requirement for any kind of spoke-to-spoke traffic, and spoke-to-spoke traffic would actually be detrimental from a security and a routing perspective, because if people are plugging in and they're pointing their remote access VPN client to a head end somewhere, to a concentrator behind the head end, it didn't really make sense. And thinking about using OSPF in an environment like that, of course, you can do some tricks with static routing and LSA filtering, but ignoring those, EIGRP was a really appropriate fit, in my opinion, because it happened to be a DMVPN interface, so effectively one multi-point interface at the hub with kind of point-to-point style interfaces at the spokes. And it's a really natural fit, because if you design it that way, you don't even have to put in any filters or anything, because the routes from the spokes get advertised to the hub. The hub pushes his head-end subnets down, but the spoke-to-spoke routes don't get reflected because Split Horizon's on by default. So literally, you can build this network, meet all the routing and security and filtering requirements with basically no config. And then EIGRP stub for good measure on the spokes. But for effectively no config, you can design a WAN that's almost 100% solution. And I thought that was a really good use case. And it was EIGRP v6, by the way, no v4 on this network. So it was an interesting use case to show kind of a protocol invented 20 years ago, extended for IPv6, that worked with almost no configuration and no effort. And I would consider it, kind of like Russ said, if you're going to do real design, you can make EIGRP, sing and dance. But in this particular thing, the real design was quite a simple option, even at the end.
Yeah, that's really interesting. I've never heard someone using the whole Split Horizon thing as a design feature, right? I understand why it's in place to protect ourselves from or protect us from ourselves and to not, to avoid loops. But I've never heard that as like, hey, that's actually something that benefits us. The fact that it won't advertise us back out that link. Yeah, that's actually really cool.
Yeah, in a secure environment like what Nick was talking about, where you're red to red and you're talking about IPsec SAs, you clearly do not want spoke-to-spoke traffic, because that traffic just gets black holed or tossed, or it's not valid. You don't want it there. So the Split Horizon really works in your favor in that case. It's pretty interesting. And Nick, what you were saying about EIGRP being modified, one of the interesting things about EIGRP's design that people don't realize is that EIGRP is not a single protocol like OSPF is. It's actually a transport section that is built underneath the rest of the protocol. So in reality, the way EIGRP works is the entire transport code is a separate code base. And you can actually modify the transport code base to work on any transport you want to. And then you can actually run TLVs like you do with ISIS, or address families like you do in BGP, to run multiples on top of that transport. And it's weird because it was designed this way because if anybody remembers this, there was this thing called ISO egrep, and there was this thing called Novell NetWare, right? And EIGRP was one of the first multi-protocol routing protocols that could support every address family in the book. If you wanted to run ISO and IP on the same network, EIGRP was your only choice. If you wanted to run IPX and IP on the same network, EIGRP was your only choice, or you had to run two routing protocols. So from the beginning, it was designed to do that kind of thing, which is pretty interesting, considering that it is a really old protocol. That the environment at that time was such that it's very flexible in those ways.
That's really cool.
I was going to say you can see that. So I was doing some reading and prepping for the show, and specifically on like EIGRP over the top, because it's just one of those topics that I didn't know a ton about. And I was reading about it and realized that you could have multiple potential overlays with different address families, all with the same peering topology. And I'm like, whoa, this looks way more like like BGP than how I understand EIGRP. And so you can still see hints of that even in the newer
Yes.
The newer features and things that are able to be implemented in EIGRP, using that ability, that separation of transport versus
It's unfortunate we couldn't get Donnie on the show, because it was kind of funny when Donnie decided to do communities instead of tags in EIGRP. He literally copied the BGP community code from Cisco IOS and put it as files in EIGRP and compiled it in with hooks. It was literally the same code as the BGP
exact same code.
It was pretty funny. It's like, okay, well,
Neat. All right. So let's talk about some of the unique challenges in deploying and operating an EIGRP network. I mean, in a lot of ways, when I think of EIGRP, I think
Sing your little song,
it's I know. You don't want that. You really don't. I think in general, in most of our networks, EIGRP is pretty solid and straightforward. Like there's not a whole lot of magic involved with it, at least in my experience. So what are some things we should look out for if we're running EIGRP in our networks?
I can say one thing is something that I've noticed in the environment where I work, specifically in military networks. What you tend to end up with is, even in Hubspoke networks, where the vast majority of traffic flows kind of goes north-south. Sometimes what you'll have is, and I know this is probably very rare in fixed enterprise-style networks, is that two spokes might be routers and trucks, and they might drive up to each other, and they might run a fiber cable between the two trucks. So now you have like a triangle-looking network. Well, if those routers are configured, for example, with EIGRP stub or some kind of outbound filter that only permits their local routes, when one of their WAN links fails, you expected that, we're connected over this fiber. If we back each other up. If my WAN fails, I should be able to route through you and vice versa. Well, that doesn't actually happen. So when you're doing things, and there's a new feature called the stub site where you can work around that, but ignoring the nitty gritty features of Cisco code releases. Environments like that where I've seen issues is when people, you design your network right. People thought about where the stubs were going to go. Everything made sense. The network worked, but then you end up with cases like this that people do these kind of sideways connections, and your reachability through the WAN is broken now. And that's something that I experienced when I was downrange. And the immediate solution is, turn off stub. And that's fine. You can do that, and it works for a little while. And if you do it as part of a procedure, hey, the two of us plugged in, the two of us disable stub. That's a minimal impact versus disable it on all 1,000 nodes.
Yep. As a matter of fact, Nick, that does come up when you have L3 VPNs or something like that, or even SD-WAN, where you're actually doing a hub and spoke network, but you have a backdoor link of some type, right? Whatever that backdoor link might be, whether it's a cable connection or an MPLS or whatever the case might be, you have some backdoor link. Well, when you get a failure on your primary link, you just expect things to fail over. But if you've done your filtering wrong or you've done stubs, things don't work the way you think they should. So it becomes an issue. The other issue is what I talked about in the first place, which is having more paths available in the network than the max paths in your routing table. And that's a design issue that people don't understand. It's a link state protocol, it's a distance vector protocol, right? So distance vector protocols just have this property, and you've just got to know that's a problem. The other thing that's the biggest design issue that you always hit in the EIGRP is that the query range is the primary design problem in EIGRP. You design the entire network around query range. That's it. If you get query range down, the entire network works. If you don't get your query range down, it's going to blow up. That's just the way it is. And so a lot of people who are designing networks, they think about summarization, they think about all this other stuff, but what you really need to think about when you're doing an EIGRP network is how you manage the query range. And so if you manage the query range, you're happy. So those are kind of the gotchas to me, is I see people who don't really think about query range. And then what they do is they set their SIA timers up. Don't ever set your SIA timers up. It's like, if you can't design the network without setting your SIA timers up, you don't know how to design the network right. I'm sorry, but you got to stop doing that. Because all the SIA timer is it's how long you are willing to allow your network not to converge. That's a bad thing. Don't do that. It's set to an absolute maximum already. Design the network correctly and don't do that. So those are kind of my gotchas that I always deal with the EIGRP.
Yeah, and then one minor point, I just want to clarify. I think Russ said something really important there is, there's a lot of focus just in networking in general on, we need to do our IP subnetting plan right, and we need to do our summarization right, and we need to do an OSPF, we need to do our area borders right, and that's all important. But the query range and the query scope, whatever you want to call it, is the main driver for EIGRP. Now, even though stub, summarization, and filtering are all common tools used, it's just a focus. It's what problem are you trying to solve? You can focus on putting summaries in the network, but where are the summaries going, and where are the slow links where queries need to be stopped? Because if you just draw your network and you just pick, okay, well, every router that's at the very edge, I'm going to put stub on that. Don't do that, because there might actually be routers that are maybe one hop away from the edge of the network where stub makes sense. Here's a perfect example. Suppose you have a small branch site over a WAN with 2,000 spokes, and that branch, you got a router that's terminating your IPsec tunnel, but then beyond that, south of it, you have a layer 3 switch that's running EIGRP. Do you really want to make that switch a stub? Maybe it makes sense to make the router a stub. That way the router doesn't get queried from the hub over the WAN, because who cares if you query the switch? It's on the LAN. So in that case, you would maybe want to do some leaking of the routes that are connected to that layer 3 switch. But in that case, we didn't put stub at the very end of the routed network. We put it one hop above, because again, what problem are we trying to solve? We're trying to keep queries off the WAN so that we can converge the network. That's what's going to bound the query domain. So just things like that to keep in mind is don't just be like, oh, I'm going to put it everywhere where I think it makes sense, and this is where the document told me to summarize. I think, like Russ said, if you're going to do proper design, make sure that you consider what your query scope is, and then use the tools to solve that problem. Don't just deploy the tools because you're supposed to.
As a matter of fact, before we had stubs, one of the common things we did with hub and spoke networks was we would actually throw 4 routers as the hub routers, and we would actually back in, so we'd actually have 2 layers of hub routers, just so we could block the queries from going across the hub and spoke network. So it was a hardware way of solving what stub actually solves today.
Interesting.
Yeah.
I've seen some funny behavior as well if you don't summarize carefully, especially with active, right? Because active is all about the prefix. And so, if I lose this prefix and I start searching for it, I saw some really funny behavior where you have more specific prefixes coming out of one link than another, and you lose that link, and all of a sudden, even though you have a backup prefix, you have something that's less specific, you still go active for those prefixes that aren't there. And so more specific routes is something that we would use, maybe in BGP that, as a backup mechanism isn't as clean in EIGRP because of that whole active query mechanism that goes there. And I saw some really quite interesting behavior with that.
Yeah. So again, think about your query range on a per prefix basis, and think about where you filter and aggregate and use stubs and other things so that you block, you're not just assuming that things are going to work right. You really have to think about the failure modes and try to understand what those failure modes look like. So it is, in some ways, it's harder to design any EIGRP network than it is OSPF or ISIS because of that. In some ways, it's easier. In some ways, it's massively easier. But in some ways, it's harder. It's a different mindset.
I see OSPF as something where you need to tweak the knobs more. I see EIGRP as the more knobs you tweak, the harder it gets. Right. And so the more you're trying to design an EIGRP network, the more complicated it becomes. Yep. Now, I'm not saying that to dissuade you from designing it, because you should, but it's just one of those things you keep in mind, that as you add summarization, as the network becomes larger, as you add stub, like it adds complexity that doesn't exist in the default deployment, because the default deployment for smaller networks is beautiful. It's one of the easiest things to implement in the world. You just, like you said, just set it and go. Yeah. But as the network grows or special conditions are met, all of a sudden there's more design, where I feel like you have that design requirement up front with some other protocols.
Right. Yeah. Phil's been very quiet.
Well, I was actually going to mention that, going back to Nick's point, it's not necessarily even the size, although I do agree with you, Jordan, but a 1,500 site DMVPN, you can still have a pretty simple EIGRP configuration over the top of that. So to me, it's definitely the use case. And that's a network that I worked on. It was 1,800 sites, with a dual hub. And when I started at that place, I expected to see hundreds and hundreds and hundreds of pages of configuration, and you log into a head-end router, or you have one of the larger spokes, and it was very surprisingly simple. At least the router configuration part. Some of the other things were more complex, and that was really surprising to me. So I think it's a lot of the use case, specifically the one that Nick brought up. A large DMVPN, even in a dual hub DMVPN, a really straightforward EIGRP configuration can be just fine. So.
Yeah, I think one of the things that makes EIGRP a little tricky, and I think I agree with what Jordan and Russ were saying, and I'll paint kind of a comparison to OSPF. We think about at a high level what is an area boundary or area border router. If I do a summary there in both directions, it's pretty straightforward to say that traffic is. I realize there's not queries and things like in OSPF, but suffice it to say that if you put a summary boundary in OSPF somewhere, that summary boundary is kind of hard. It's right there. But with EIGRP, it's a little more sneaky. So let me try to paint a picture for you. So suppose you had 4 routers in series, R1, R2, R3, R4. Just kind of picture that. And suppose that this first router has like 4 LANs connected to it. So 4 user subnets, 4, /26s, they aggregate into a /24. So R1 takes these 4 routes, and every EIGRP is enabled everywhere. So R1 advertises these 4 routes to R2. So R2's got all 4 of these routes in his routing table. Great. Suppose that R2 configures a summary towards R3. Okay, so R2 has 4 /26s in his table. He goes on his port to R3, says do a summary for /24. He ports that off to R3. Okay, so we move over to R3, we do show IP route, we look at what he has. He's only got that /24. And then he sends that on to 4. Okay, so we should have reachability in this scenario. The question becomes, suppose I go on R1 and I shut down one of those /26s. How far does the query go? And this is the question I think a number of people would probably not understand this is when one loses that, he has to query R2. Because he was learning the route from connected. It was his local route, and he says, well, I lost it. Hey, R2, do you have another path to it? R2 is the person doing the summarization. So some people might think that R2 is a summary boundary. He's just going to immediately reply to R1 and say, no, I don't have another path, and the query domain is bounded. That's false. What R2 does is he has to query R3 because remember, R2 has all the routes. R2 has all 4 of the routes. He configured the summary. The query goes what I'm really trying to get at here is the query goes 1 hop past where the summary or the filter is configured. Yep. So the query will go to R3. R3 is like, well, I never had that route. No. So R4 is the only router in this network that doesn't get queried. So the reason that's important, though, is again, what if that link between two? What if the link between 1 and 2 and the link between 3 and 4? If those were high-speed gigabit links, but that link in the middle was a slow WAN link, this is probably not a good design. Maybe doing the summary at R1 would have been the superior option. So you have to. That's kind of goes back to what Russ is saying. Understanding the nuances of the technology and how the query scope works. Like with OSPF, it's easy. The boundary's right here. It's kind of straightforward. You can look at it and understand it. But with EIGRP, it's sneaky. You got to understand what routers have which routes, where do the summaries and filters occur, and how far does the query go? Because that's going to become, again, kind of to Jordan's point, when you're doing this level of EIGRP design, you need to be really think through those locations where you do the aggregation and the filtering, because the query domain is going to go one step beyond that. And you need to keep in mind, if that next step is an extremely slow link, then that might not be a good design option.
And this, by the way, is a really good example to me of thinking through design from understanding the theory of how the protocol works, rather than just how you configure it. I think this is a really, really good example of that type of problem because, EIGRP queries end where the information is no longer available, not where the aggregation stops. It's where the information is no longer available. And that's what you have to think about. So, you have to understand that's how EIGRP works when you're designing the network. You just can't go, well, I'm configuring the summary here, therefore the information is no longer available, therefore I've solved the problem. No, you really can't. You've got to really think about how this protocol works.
I'm really glad you guys brought that up because I'm thinking about networks I've worked in and how many times the summary happens before an international link. Right? Yeah. I'm going to summarize across this international link, but the query goes across the international link anyway because it's one step beyond. Yeah.
Yeah, that's exactly right.
Yeah.
And so that's why before we had stubs, we would throw the 4 routers in as hubs. We put a 2 deep hub situation in. So the query would stop at the router above the hub router rather than passing to the hub router and going beyond the hub router. Yeah, so that's a tip. I mean, that was what we used to do before we had stubs. We used to play all sorts of tricks like that.
Yeah, and then extending that same concept, like Jordan, your example of that international link, if the concept of hierarchical summarization is probably easily understood by all of us talking here, but the idea there would be almost the same thing that Russ is saying is before the routes even get to that international ASBR in your network, it's there's a I don't say an assumption, but a design choice to have done lower level aggregates before it gets to that point. So those individual LANs failing or remote sites failing would have been masked by that international router in the first place. So the hierarchical aggregation, and again, kind of the the big misnomer of aggregation is that it keeps your routing table small. That's technically true, but it's typically not the driver. The driver, again, like Russ said, and it's worth repeating multiple times, is scoping the query domain. And aggregation is a great tool to do that.
Yep, definitely. Yeah.
Nick, I think we're going to see some GNS3 and viral fired up tonight based on that. As you are going through router 1 and router 2, I'm like, oh man, I wish I had a pen and paper.
I hope that's what happens.
I tried to draw the simplest possible example I could to demonstrate it, and that was the simplest I could come up with in 2 minutes.
No, that's good. I have a feeling. I have a feeling though we're going to see a lot of folks, I hope maybe in the comments here, with some folks lapping that up and playing with it. So.
Yeah, and while we're on that topic, there's one more, and this is a question I've posed it a few times in some study groups that I'm part of, and Russ has probably read through it a few times. Here, it's kind of another thing that I'm going to talk through, and you're probably, if you're just listening, you may not be able to visualize it really well, but it's kind of, this is, I think by now most people kind of understand that the EIGRP stub, so I guess it's worth backing up for a second. Let me just take a quick break to the side. And for people who don't know what EIGRP stub is, I'll give you the 15-second version. When you configure an EIGRP router as a stub, kind of 2 critical things happen. Number one, that router can't be used as transit because it only advertises it's connected in summary routes. Generally, you can adjust that, but so it's not a transit node, so it makes sense for a spoke or a top of rack switch in a data center fabric, something like that. And the other thing is you can never query a stub router. So a router cannot be queried ever. So that information, the presence of being a stub is present in the EIGRP exchange with a neighbor. So if I'm a hub, I was like, yeah, these 10,000 people, they cannot be queried. I will never send them a query. So that's kind of what a stub does. That's one way to bound the query domain. So I want to just kind of paint kind of an a theoretical scenario, because, in real life, this network would be better designed. But we've talked a lot about using the EIGRP stub filter to bound the query domain. And we talked about using summarization and filtering to do the same. And the reason that it's worth talking about this for a good chunk of the show is because it is literally the #1 driver for EIGRP, and that's probably worth discussing. So I just want to paint, again, a quick scenario here. Suppose you have a single hub and 3 spokes, such as the Hubspoke network, like a crow's foot kind of network. You are trying to, let's just assume you have some kind of instability and some issues with queries. I don't give you a whole lot of information. I'm a junior engineer, and I tell you that. You're given the choice to either issue a summary route, like a default, from the hub. That's option 1. And option 2 is configure EIGRP stub on the spokes. But you can't do both. So we all acknowledge that doing both is probably the best answer, but you can't do both. You can only do one. And the reason I pose this question is because sometimes you'll get people who just blurt out one of the answers, whichever one they like more, and that's usually not the way to go about it. And I think it's worth just talking through kind of the logic behind this. So let's suppose we choose option 1 and we send down this aggregate address from the hub. That means that if I'm a spoke, all the routes that the other spokes have are all covered by that summary. So in that case, if another spokes fail, so for example, if I'm on spoke 1 and spoke 2 fails, it goes off network completely. If I'm spoke 1, I will never know it. I won't know it failed, which is going to have some impact on the query. And specifically, if I'm thinking about this right, the spoke will never query the hub because he's not aware of a change in the network. So imagine I had 1,000 spokes and spoke 1,000 fails. Those first 999 won't query the hub because to them, nothing changed. Does that make sense?
Mm-hmm.
Now, but what does happen, the hub queries all the spokes because the hub is aware of the change and none of the spokes are configured as stubs. So now the spokes get queried by the hub, but not vice versa. Okay, so that's one solution. You probably see where this is going. If we do the other solution and we configure the spokes as stubs, the spokes never get queried by the hub, but the opposite is true. The spokes will query. I'm getting confused here. I'm talking too fast.
The hub will never query the spokes.
If the spokes are stubs, the hub will not query them, but the spokes will query the hub when one of the remote spokes fails. So basically, right. I'm asking the question, what direction, pick your poison. What direction do you want the queries to flow in? And it's less about getting the answer right because there isn't a right answer. It's more about thinking through kind of what I just said. And I think a lot of people kind of make the mistake of, EIGRP stub, that's what you're supposed to do. Well, just take a second, breathe. And think through that because when we talk about summarization and stub together, that's where you get the power. But when you're only forced to choose one, and in some networks that might be the case if you're using maybe a standardized version, somebody wrote EIGRP in Quagga or whatever, and it doesn't support stub, well, then maybe you're only stuck with one choice and you have to choose one, but you should be aware of the impact on your network. and what tool is right for the job. And again, in that particular case, both tools make sense. But I just wanted to pose that as a kind of a theoretical discussion scenario, because I think it highlights the thought process through how does the EIGRP network converge when there's a failure, and how do the different tools work in a common Hubspoke network.
Yeah, I think it's important in all routing protocols to think through the failure modes. We often think through how it's going to work, but we don't think about how it's going to fail. Like, oh, I build this network with a ring of 6 routers, and I don't really think about how OSPF or ISIS or EIGRP converges on that topology. So I just go off and I build this thing, and I just assume it's going to work. Good for you, but think through the failure modes. It's really important to think about what happens when things fail. And this is true of all routing protocols. But Nick, did want to interject one thing. It's not Quagga. Don't quag it.
Oh no!
No! I had to pick something.
I know. No.
If it's free range routing. If you have to pick one,
yes. If you have to pick one, free range routing, because there is actually an EIGRP implementation in free range routing that is an open source implementation. It's not perfect yet. We're still working on it, but there is an open source implementation in free range routing.
But I think Russ's point is well taken about thinking through failure modes, because none of us have been on the phone at 3 a.m. because our routing protocol is working normally, right? And so...
Really? That's never happened to you, Yvonne.
I mean,
although you know what? Now that you said that,
case.
I might actually welcome one time that call. Right? Like I just wanted to call you and tell you that the network is operating perfectly. Thank you.
But it's never good to think through those failure modes for the first time at 3 a.m. Right? And so understanding how it's going to fail and what to expect when it fails is a hugely important thought exercise for us as network engineers. So,
if you have the luxury of a greenfield design and deployment.
No, I think
you can still do that. I mean, you can still look at the environment and say, what happens if this link fails? What happens if this route goes away? I mean, you may not be able to do much about it, but at least to have that in your head, because at 3 a.m. it doesn't work.
Well, I mean, not even 3 a.m., Yvonne. I mean, when I was on global escalation and I would be dropped into a network and I was given a network diagram that was, 15, 20 pages printed out or larger or whatever it was, one of the things I did to try to understand the network better was to think through the failure modes. Not even this particular failure that I'm working on. Just say to myself, all right, if I want to understand how this routing protocol works in this network, I need to think about what that failure would do to how it would converge about this failure, because that helps me think through where they've done aggregation, like what Nick is talking about, right? It helps me think through where they've done aggregation, where they've split up their failure domains, and makes me double check, like, do I really understand where those failure domains exist and where they don't? Or am I just going, oh, that's just an ABR, or oh, that's just an aggregation, so boom, I know where it is? Not necessarily. There are places where you split a failure domain, but there's a backdoor. Oh, so you look at the aggregation, you're like, oh, it's aggregated, so therefore there's 2 different failure domains. Well, not necessarily. There could be another link. Again, going back to Nick's example of the 2 trucks pull up next to each other and connect a fiber cable between them. Now my failure domain is different than what it used to be. And unless I'm thinking about that in terms of failure domain, and I'm not going to see that unless I really think through how this network converges. And I think that's where it's really helpful to do that. So anyway, that's just kind of that's one of my escalation engineer tricks. Was I always went through and when I would sit down with an IT team that was working on a network that was failing or was trying to figure out how to design something, was always, all right, what happens if I take that link right there out? Tell me how the network converges. And when you do that about 10 times, all of a sudden the light bulbs start going on in people's eyes and they're like, well, now I see how this network really works. Yeah, that's very helpful. So that's kind of my take on that entire.
All right. No, go ahead.
Oh no, so because just another point, and Russ and I have actually talked about this quite a bit in the context of fast reroute and fast restoration. EIGRP is pretty well known for the idea of a feasible successor, so effectively a fast backup path. It made that cool before the other protocols made it cool, and that was kind of I wouldn't call it quite as big of a design driver as the bounding the query domain, but it's probably one of the bigger ones. But the interesting thing about it, it's probably not worth talking about the math and the formulas on the show. But the interesting thing about that, and Russ I actually argued with Russ 6 months ago because I didn't understand it. So I'm gonna explain it the way he explained it. And he can back me up if it's wrong, because it made a lot. Because my thing was I was actually trying to develop a way that EIGRP would be able to use backup paths that where the feasible distance and the advertised distance were the same rather than strictly less than. And my Russ has said, well, that could cause microloops, and I just didn't believe how that was possible. And he painted a really easy scenario that kind of explained it. And again, I realize I'm drawing diagrams with my mouth right now, so it's a little hard to follow. But the general idea,
wave your hands.
wave your hands. The general idea is, if you have kind of like suppose you have like an isosceles triangle where router 1 and router 2 have a really, really fast link, low cost between them, and then they both have, maybe WAN links out to R3 that's kind of far away. So if you want to draw it to scale, it'd be like kind of a isosceles triangle that way. If one of those WAN links fail, if you think about, if R1 sending traffic to R3, but the link between them fails, I feel like R1 could just route through R2 and have it be a fast backup path. When you think about cases like that, but the problem is that doesn't work, because what if R3, the whole router fails? If the whole router goes down, then R1 and R2 are both using each other for backups. You have a microloop. So EIGRP was specifically designed and said, we acknowledge that if the feasible distance, my neighbor's advertised distance are the same, and I use that for a backup path, it will work in some scenarios, but in others, it causes microloops. So if I understand it correctly, Russ, the decision was, we want EIGRP to be different from the link state protocols, and we want it to guarantee that there will never be microloops during a convergence event with EIGRP based on the way the feasibility condition was written.
Yeah, it's actually the opposite. It's actually EIGRP was designed to never microloop. It was the decision was made consciously that the way the feasible successor process would work is that it's a negative test. You know for a fact that no matter what happens in the network, if it's a feasible successor, it will never loop. Never, ever, ever. Which cuts out possible alternate paths that may also be microloops. That's why it's a more conservative test than an LFA. When LFAs were being designed in link state protocols, it was much later. Remember, EIGRP was designed in the world of X25. Right? Microloops are fatal in X25. I mean, you can take out a 64K link with a microloop in a heartbeat in a hub and spoke network with dual homed hubs and stubs and whatever. So it was intentionally designed not to ever microloop. When link state protocols started thinking about how to do LFAs, the design concept was more about, well, we're in high-speed networks. Microloops are okay for a tenth of a second, a few milliseconds or whatever the case might be. So they actually designed them to be more forgiving because they wanted a broader set of alternate links or paths with the assumption that microloops were going to happen. And by the way, the interesting thing about this is link state protocols always microloop in a large ring anyway. So it wasn't like when we were doing LFAs in link state, it wasn't like, oh, this is radically different. Now there's going to be microloops and there never were. Because there always were microloops in link state protocols. So it was just yet another instance of the same thing. So yeah, but the design, you're right, Nick, the design was intentional on both sides to choose a different way of doing things. I was just saying EIGRP's design came before link state design. So, and it's because of the link types. It's because of the environment EIGRP grew up in, basically. That
makes sense.
I just have two relevant, what I believe relevant comments. First is, Nick, you draw some of the best mental network diagrams I've ever heard.
Really good.
And second, and I never thought about it this way. EIGRP with feasible successor is the hipster router protocol. It was cool before everything else was cool. I just had to throw that in there.
Okay.
Good stuff.
All right.
It is. But,
we need to get it a latte and some black glasses.
Yeah, that's right. Some skinny jeans. Yeah.
Avocado toast.
There we go.
There are a lot of DevOps folks out there that would strongly disagree with it.
But the interesting thing about it is that even though EIGRP had the concept of a feasible successor and backup paths and all that, it's limited though, because if you look at, and again, I'm not going to quote the RFCs and the math and the different inequalities that go into LFAs, and Russ and I like to geek out on this on direct messages.
That's why we're here.
For the rest of the world, yeah. See, I don't have that memorized. I'm not going to lie, I don't have it memorized. OSPF.
Thank you for making me not feel inferior.
But I used to know
Nick,
it. But anyway,
would you like me to go? No, never mind.
Oh no, Russ, come on now.
No. But long story short, the thing about the most forgiving LFA in OSPF is one that can guarantee link protection, not necessarily node protection. But what it does, it relies on you knowing your neighbor's local cost. And EIGRP can never do that. I mean, I say never, and of course you can extend the protocol, but the point is that EIGRP is aware of its local cost and the routes from the neighbor, but you don't know your neighbor's local distance, his local cost. You'll never know that in a distance vector protocol. So because I don't know his cost, I don't necessarily know if he's going to route through me or not. I don't have his picture of the
exactly
network.
Right.
So EIGRP's LFAs, even though there's like a new little switch on the command line that says EIGRP fast reroute, all that does is take the route from the routing table and write it to TCAM faster. It doesn't actually change the process. It doesn't actually change the way LFAs are built like it does in OSPF or IS to IS. So just, kind of keep that in mind. Is EIGRP fast reroute's not really a new thing. It just uses feasible successors in a way that converges, milliseconds faster on chassis boxes kind of thing. But EIGRP is kind of, we kind of came to that natural conclusion with feasible successors based on the design of don't microloop.
Right.
While the other protocols have kind of more knobs that you can turn for more customized, I won't say customized, but more better backup coverage, better LFA coverage, both in rings and general topologies. So that's not something you're generally going to get with EIGRP.
Right.
Yep,
So long as you're willing to live with the microloops, right? Your basic choice is throw the traffic on the floor or microloop. Those are the only two choices you have. EIGRP made one choice, link state protocols made another. It's just the way it is.
Yeah, and I dare say, if we're talking, and this is kind of a hard claim to make because networks tend to be more general purpose, but if we're talking about applications and business requirements, and let's just say magically you had a network that had a lot of voice traffic and packet loss was an issue and the voice flows were small and the links were fat, then microloops might not be a problem. So OSPF and IS to IS without LFAs might be an appropriate option because having that packet loop a little bit on a link and have its TTL decremented by 40 doesn't really matter because that packet's still going to make the destination and the voice quality is not really going to be measurably hindered versus dropping the traffic could be a more serious issue, maybe stock market stuff. I'm kind of just making this up as I go, but the applications might have some impact on the routing protocol in that case when you're talking about things like, do I microloop it or do I not? If you're in the data center with extremely heavy data flows and relatively shallow buffers on giant routers and switches and stuff in the data center fabric, and microloops are a bad thing, you'd either want to go something like a link state protocol with ordered fib or LFAs or EIGRP. Yep. So just some things to kind of keep in mind how application
or BGP. This is actually one reason a lot of people use BGP in data center fabrics because it doesn't microloop either. And so it's actually seen as a net positive for BGP that it doesn't do this. It has other issues though, but yeah.
All right, so we've talked about the details of EIGRP, but let's talk about its future. What do we think is going to become of EIGRP? We know it's a mostly Cisco proprietary protocol. They've released stub features to the IETF, but what do we think is the long-term view for EIGRP? I know I've heard vendors. Other vendors, non-Cisco vendors, say, you just need to get off EIGRP because nobody else does that and the world's moving a different direction. What are your thoughts on that?
I would differentiate between EIGRP and dual. So that may sound weird, but one of the problems we have in the modern routing world is we tend to think when we say EIGRP is dead, we tend to say, oh, because EIGRP is dead, distance vector is dead, and I would disagree with that. I think distance vector itself has a very bright future in many ways. EIGRP itself, there are open source implementations out there now that are being worked on. I know of people who are starting to seriously consider it in certain environments, particularly mobility type environments. And there has been some talk in data center fabrics of doing something like EIGRP. In the dual world, in the larger world of diffusing update algorithm, there is an actually new protocol out there called Babel, which I'm a co-chair of the working group in the IETF for that. And it is a diffusing update algorithm type of protocol, which has a lot of really neat features in it. It doesn't have everything. It's kind of overlaps with the EIGRP. There are things that are better than EIGRP and things that are worse than EIGRP in Babel. So overall, I still think that it's a viable technology. I think we've gone through this hard pendulum swing to link state, and eventually, as networks always do, we tend to pendulum swing back and forth. And I think we'll start seeing action on the EIGRP front at some point in the future.
Yeah, and that's a good point. I think it's worth. I'm going to try to summarize what diffusing update algorithm means in about 30 seconds, and see Russ can probably correct me, but I'm trying to keep it quick. So
he's our interpreter.
The reason it's called that is because the word diffusing is really what we're trying to do is you think about EIGRP, and I go on a router and I look at an EIGRP topology table. The only state in that router is the state for myself and my directly connected neighbors. I don't know about anyone else's state. It's not like link state where I have this massive area or flooding domain like IS to IS or OSPF where I have a lot of state. The only state I have is for my neighbors. So the state gets diffused through the network at every hop. I'm only sending pieces of the information like the route, basically the route and the cost to reach it. That cost is a composite of multiple different things, as we know, bandwidth, delay, load, reliability, et cetera. But the idea behind the diffusing update is that I only have state for my peers, not the whole network, so that my scalability of my table is ignoring the size of my routing table and the memory to retain it. The stage of my EIGRP state is limited to a very small number, typically single digits, maybe double digits of EIGRP neighbors. So that's one of the scaling aspects of EIGRP that's just built into the way it works, is that you can have tens of thousands of node in one EIGRP autonomous system. Generally, in OSPF or IS to IS, you can't really do that within a single flooding domain. But with EIGRP, you could, given, again, intelligent query domain scoping and all the other design considerations that we've kind of talked through. So that's what diffusing update means. So did I get that right, Russ?
Yeah, but you not only diffuse the state, and this goes back to the state optimization surface, doesn't it, Nick? Anyway, you not only diffuse the state, but you also diffuse the convergence process, right? That's what the query is doing. It's actually diffusing the update process. In link state, every individual router makes its own decision. In a dual-based network like EIGRP or Babel, you're actually sharing the work of converging on new paths among all the routers in the area around that failure or that new route. So it actually diffuses the work across multiple CPUs. So the diffusing kind of plays in multiple ways. So I would say that, again, that whole concept is actually still a very valid concept. We don't use it a lot, but it's still a very valid concept. It gives you a different set of trade-offs than link state does. And I think that it's important in the networking world to never let go of an idea like that and to find places to use it in the future, because, as I said, pendulum swing, eventually it'll come back. Babel is very heavily used in mobile ad hoc networks and home
Rule
networks.
11. It's Rule 11, Russ.
Yes, I know it is Rule 11. There you go. My favorite RFC 1925 rule.
Throw in a significantly less technical perspective here. I did a project recently where we were required to use OSPF instead as a result of our SD-WAN solution and as a result of the possibility that we wouldn't be using Cisco in certain parts of our network, specifically the WAN in other areas, but obviously our SD-WAN. And that in and of itself was the driver to not choose EIGRP, if that makes any sense, and I'm sure it does.
No, I understand. I can understand and appreciate that. I think the only thing I would offer in that case is asking the golden question is, what's the problem you're trying to solve? And if you have, let's say you had a WAN that was non-Cisco, but you had Cisco equipment in other places in the network, it could be very tenable to just run different protocols and have some kind of interworking solution between them, like redistribution or BGP between them, or those are options that I think a lot of people kind of turn their kind of cold shoulder those ideas and say, well, we just want to have one protocol everywhere, and if we have to do OSPF areas, that's fine. But I would also just encourage everyone to kind of think through what's the right tool to solve this problem. And if you're talking about a relatively small Hubspoke WAN that OSPF can scale over, it's not that much of a problem. The broad brush in general, kind of like Russ talks about these massive pendulum swings between ideologies, that's generally not the best way to go. And I'm certainly not suggesting that was your idea, but just as a general comment, the broad brush approach to one tool for everything is usually not the right answer. So I would say deploy the right protocol that makes sense in parts of your network, acknowledging that redistribution can be kind of a nightmare sometimes, but used intelligently, and especially with intelligent summarization and preventing loops and things like that, it can be a pretty powerful tool. And oftentimes, especially when you're working with things like OSPF, breaking up the flooding boundaries with external routes, if you redistribute OSPF and EIGRP, that guess what? You broke the query boundary for EIGRP in doing that. So there are some advantages there to consider. Individually, how did I help OSPF and EIGRP? And overall, how did I help the business case or the business drivers for the network by deploying the right protocols in the right spots?
So the other thing is, Phil, you can go back to that vendor and say there is an open source implementation you can back into. There's no reason for you not to consider using EIGRP in the future. No, seriously, I do think that as network engineers, for some reason, and I don't understand this, maybe it's just my personality that I'm not this way, but we tend to have this feeling that we can't push back on vendors and we can't push back on business people. That we're just not, we just have to take what's given to us and make it work. And I am so against that. To me, if a vendor comes to me with a solution and I think the vendor solution is horrible, or if I work for a vendor and a customer says to me, I'm going to do this, even as a vendor, I'm going to say, no, that's a bad idea. Let me try, we need to work together to make the solutions better. We don't need to say, oh, well, my manager told me to do this. Yeah, great. But as an engineer, I need to have enough confidence, and I need, not just on the engineering side, but on the business side, to be able to push back and say, no, it's not a good idea. I'm sorry. And trust me, I've gotten in trouble for this, so I understand where it comes from. But I do think that, seriously, if I was in that position, I would go back to the vendor and say, all right, for this deployment, I understand why I need to do OSPF. And I know that you're not going to deploy EIGRP right now, but I'm going to tell you as an engineer, there is an open source implementation of EIGRP. You really should look at this for these large scale hub and spoke networks, and you should really be giving your customers other options. So, that's just my kind of take on that.
That's Russ's hoorah speech to tell us all to fight the good fight.
That's right. There you go.
All right, guys, we are going on an hour here, and it has been a really great conversation. I may have to get out my GNS3 lab here in a bit and do my R1, R2, R3, R4 that Nick demonstrated for us. So real quick, Jordan, why don't you tell people where they can find you on the web?
Sure. I'm at BCJordo on Twitter. I blog occasionally at jordanmartin.net.
All right. And Phil?
You can find me at network_Phil on Twitter, and networkphil.com is the blog.
All right. And I'm Yvonne. You can find me on the blog at esharp.net and on the Twitter at the Twitter, the article, whatever, at Sharp Network. And so we're really grateful for Nick and Russ joining us today. And we will be back again in a couple of weeks. We've got Cisco Live coming up in a few weeks. So we'll have some special recordings from there too. So thanks, everybody.